Okay, it looks like we have a good amount of people already. I'm going to go ahead and get started. I'm happy to welcome you all to today's webinar, Harnessing the Power of Vectors and AI to Build the Next Generation of Intelligent Apps. Today we have Steve O'Grady, Principal Analyst and Co-founder at RedMonk, and Benjamin Flast, Product Management Lead at MongoDB, who will be hosting and answering your questions in the Q&A panel. A couple of housekeeping notes before we get started. This webinar will be recorded and shared. All participants will be muted. We also invite you to ask questions in the Q&A panel. The chat will be for just general discussion only. Now I will hand this off to Steve O'Grady to begin the presentation.
Outstanding, thank you. So if we go to the next slide, as stated, I am Stephen O'Grady. I'm the co-founder of RedMonk. RedMonk, if you are unfamiliar with us, is a developer-focused industry analyst firm. What that means in practice is that we are, we research and write on technology subjects with the lens of, sort of concerning ourselves with what practitioners are using, right? So the practitioners could be developers, it could be DBAs, it could be sysadmins, operators, and so on. If you're in the trenches building technology, we're trying to understand what you need, what you're building, why you're using it. And certainly in recent quarters over the past probably 18 to 24 months, what we have heard over and over from developers is the need for and the demand for and the usage of vector databases. And so what I wanted to do today was talk to you all about what they are, what they're for, what they're good at. And obviously, as this slide says, in simple terms, why your database needs to support vectors. So we can go to the next slide. So before we get to the vectors themselves, it's useful to understand a little bit of context here, because that will sort of inform the bigger picture in terms of why we want to incorporate it into existing databases. So for many decades, as many of you probably know and have lived, relational databases were the default, right, for basically every application, to the point where internally at RedMonk, we, sort of the joke is, relational database is the answer. Now, what's the question, right? And, what happened, sort of over the, last 2 decades plus is that as workloads scaled out and new models, sort of emerged, right? Most obviously the web, mobile as well. New database models were required. Relational databases have many strengths and, will be around, probably until the end of time. But, we needed new models to address the areas where they were less strong. And so beginning in around 2009, there was this Cambrian explosion of database types, right? So, all of you, sort of on this Mongo webinar are likely familiar with many of these types already. Document, most obviously, search, streams, data lakes, but the list goes on, right? Columnar, key value, and so on. We had this explosion in types. We'd gone from areas where, everything was a relational database to, there were, half a dozen to a dozen credible new categories of databases. And these non-relational databases were all referred and bundled into a new category. Speaking personally, I didn't think that the term that the industry picked was all that useful. Particularly given that many of these databases that define themselves as not having a query language subsequently went back and added a query language. But that's what the industry decided on. So we had this bucket called NoSQL, and we lumped in all of these different and disparate database types. So from sort of large distributed applications to these enormous data lakes, databases continually evolve to handle an ever-expanding array of new workloads. Okay, next slide. And so there's good news and there's bad news sort of about this transition. So NoSQL allowed enterprises to use the best tool for the job. That's good. And many NoSQL databases, meanwhile, were designed to be developer friendly. So many of you, who have experience, with some traditional relational database platforms may have encountered some of their rougher edges. These were originally, sort of over the course of decades, designed to be friendly to DBAs and not so much for developers. Whereas the tools that came up, in the last, 10 to 20 years, were built in many cases by developers to solve these new challenges, these new workloads, and therefore were more developer friendly by design. So what ended up happening was that we had a transition, and enterprises went from these models, right? That these models for infrastructure that were dominated by DBA oriented relational databases, and began to incorporate developer friendly multi-model infrastructure. And what that meant in practice was that rather than have one database, a relational database, sort of at the core of a given sort of application infrastructure, we'd have many databases of many types. And that, again, it's nice to be able to use the best tool for the job, but the diversity came with costs. For the from the perspective of the enterprise, there's more vendor relationships to manage, right? If you're going from, hey, I have one vendor relationship, or one vendor, relationship to manage for a type of database class, and then I multiply that because now I'm using sort of many more projects, that can be difficult to manage, from the enterprise procurement standpoint. More importantly, from a developer standpoint, this is just more interfaces to deal with. There's more cognitive overhead and switching between, sort of these individual platforms. And, sort of lastly, you have more integration points, right? So rather than have sort of one key platform to store, you have a bunch of different, key platforms that are storing data. And these, integration points need to be maintained, sustained, operated over time. And so what we're seeing today, what we're going out and talking to all the developers that we do, and talking to the business and talking to the vendors that are supplying the businesses with technology, what we're seeing sort of across the board are enterprises are beginning to prioritize single data platforms that will support multiple workloads over the alternative of multiple specialized databases. So they have not given up on the, we're not returning to the everything is going to be relational, and that's the sort of end all be all. We are continuing to see demand for, essentially specialized engines and specialized tooling to deal with different workloads. But the desire from an enterprise standpoint and a developer standpoint, as well as we'll see, is for a single data platform to support this. So if we go to the next slide. So this brings us to vector. So as we talked about before, we had this explosion, sort of in data types, over the last decade plus. We had all these new sort of categories emerge, and vector is the most recent of these. And as we saw with the NoSQL generation of databases, vector emerged to solve new problems, right? So we have machine representations of data sets, and we'll talk about what that means in a little more detail. Like image, voice, or text, or even molecular structures, right? Vertical use cases as specific as that. These are exploding as machine learning and specific techniques like large language models are being thrown at all sorts of new problems, within the enterprise and down to individual consumer use cases, in fact. And traditional databases, meanwhile, they're just not structured to handle some of the imprecise, sort of comparative questions, that we're seeing from these systems, like which items are like this one. Now, there are ways to try to get around that. We can try to infer this, from customer behavior, and this is how retail sites have often handled this. They don't know anything about a given product, as an example, but what they can do is say, okay, customers who looked at this product, looked at these other products, so I'm going to infer from that they're similar, but they don't have any sort of native understanding of the nature of the objects themselves. And that has been a sort of key limitation. So as floods of these machine representations of data have arrived, users began to generate all sorts of new questions. And probably any of you who have used any of the conversational LLM systems, ChatGPT and Bard and otherwise, have probably experienced this. You have, you can ask it a question, and then you ask a couple more questions and a couple more questions. So floods of these new questions are arriving. And so to answer these, at least to answer classes of these questions, I should say, sort of a new technology was required, and that's vector databases. So we can go to the next slide. So that brings us to the sort of basic question of, how do vector databases work? Like, what is this? How is it different? And I'm going to try to keep the sort of explanation here accessible. So we're not going to get into sort of any of the cosine math or any of the sort of real underlying nitty gritty details. Ben will probably go into a little more detail than I will. But to give you sort of a layman's version of what they are, vector databases are used to query high dimensional data or data with many given overlapping characteristics. So the obvious question is, what does that mean, right? What do we what do we mean when we talk about high dimensional data? And the way that we typically explain this, to enterprises we're talking to or other developers, for that matter, is that if we think about, take a location like Paris, France, right? Paris, France can be located in 2 dimensions. You have a latitude and a longitude, so you can place it on a map. It's pretty simple. It's pretty straightforward. And what we begin to see with from vector databases is, okay, what if the object has more dimensions than that? What if there are many, many more characteristics, potentially hundreds, even thousands of characteristics to this? So, with a given sort of object like Paris, okay, so we have latitude and longitude, but it has a million other characteristics, right? It happens to be located in the country of France. It has a particular climate attached to it. It has a particular population and so on. And what we have seen, from the marketplace is a demand for, I need to be able to ask complicated questions, of objects with many, many dimensions. And relational databases and most other databases have historically not been particularly well equipped to answer that. So vector database technology began to emerge. And vectors are created by applying models to a given data set, right? So the example that I have in here is one that came out of a Google paper. It's called Word2Vec for text. And so what ends up happening is you have a given data set of a given type. It could be texted, images, audio, sort of you name it. And there is a model or an algorithm that is applied to that. And that is then translated into a series of numbers. Vector databases store this transformed data in vector embeddings. And these vector embeddings are completely opaque to people, right? It is literally strings of very, very large numbers. And it places these objects relative to their relationships with each other across these different dimensions. So thus similar objects are placed closely together, unrelated objects are placed further apart. And, to go back to our example, Paris, Paris, France would be closer to our vector database to other European capitals than, say, New York City or San Francisco. And that's the simple version of this. But vector databases are essentially taking these data sets, transforming them into numbers that can be worked on and queried according to a number of different varied dimensions. And sort of lastly here, the vectors are then indexed. Probably everybody on this call is familiar with the indexing of databases, but this is what makes querying practicable, because you cannot query these enormous sort of vector data sets without sort of the benefit of that from a performance standpoint. So next slide. So this begs the question, like, what kind of questions can vectors answer? Right. And this is, okay, I have a relational database, or I'm used to document databases, other database types. Like, what's different? Like, why why is vector technology necessary? What's different? And, the answer is that it can answer literally an infinite number of questions. Now, it's stronger at some things than others. You're not going to use a vector database, for example, to go and query a given customer's balance. If you're a bank. Right, we have databases that are quite adept at that, but the vector database technology is used to ask really, really difficult, complicated questions. So we have a couple examples here. So semantically, what are documents most similar to a given query? Right, and so if I'm looking for, as an example, sort of questions on a vector database, okay, where's this in a given set of documentation? Where is the documentation that's most similar to vector databases? That's likely going to turn up documents on LLM or other AI adjacent technologies, as opposed to, I don't know, documentation on the Go programming language or CSS or something of that nature. Images, what are the most similar images to a given image? So you supply an image, it will go out and query that, and it has the ability to return images based on the mathematical representation of these images. It's broken down and says, these are the most similar images. We see this in biopharma. They're asking, all right, what's the most similar drug structures to a given example? In audio, what are audio files that match this particular voice? E-commerce, and we discussed this one a little earlier. What are products similar to one purchased by a customer? And importantly, it's not inferring that, right? It has a native understanding of the object itself. In government, for example, they're beginning to use the vector database technology to analytically ask questions like, okay, what counties in the US are most similar in population, birth rate, level of education, and 5 other dimensions. And so, vector technology is increasingly being applied to, these vague, comparative, very, very complicated questions to answer. So next slide. So why should databases support vectors, right? So there's a number of reasons. The demand for AI technology in general, we at Redmonk have been doing this for a long time. We have seen a lot of technologies come and go. We haven't seen anything grow as quickly as AI-related technologies. And it's not a fad. These are real use cases. It's being deployed in production to solve real problems. And vector use cases are very broad and limited really only by customer imagination. What can you do with this thing? Really, again, you're limited by your imagination. And as with any analytical database, vector's effectiveness is tied to the underlying data. So each new data layer, or sort of more accurately silo, is a potential roadblock, for accuracy and efficiency. And developers are already swamped by an abundance of interfaces. Their preference is not for more and more individual siloed tools that they need to manage. Their preference these days is for more broadly capable platforms, that they can have a single interface for, but deploy capably across a wide variety of different data model problems. And the enterprises, for their part, as we discussed briefly earlier, are focused on consolidation rather than expansion of their portfolios. This is one of the biggest changes we've seen, sort of over the last decade plus, is that we've come from a sort of world of, primitives are, sort of rapidly assembled, everything is DIY. And we're moving more towards an environment, both from a developer standpoint, bottom up, and from an enterprise standpoint, top down, that is favoring consolidation. I want simpler, more broadly capable software stacks that I can sort of manage more effectively, that will allow me to go faster because I'm not dealing with multiple interfaces, but that are not compromising in terms of what I can do, from a technology standpoint. So if we can go to the next slide. So, really what I wanted to leave you all with today is that if you are not using vectors already, and it is likely, depending on the size of your organization, if it's large enough, even those of you who believe you're not using vectors already, it is likely that somewhere in your organization, someone is playing with them. So my guess is that you are, and even if you're not, you will be soon. And as a result of that, you want to make sure that your database provider can help. This is an important technology, is being deployed, as we talked about, against real production use cases every day, every minute. And it is incumbent, therefore, on your database infrastructure to be able to help, sort of in this fashion, rather than saying, hey, this is not our concern, go figure it out yourself. And on that note, I will turn it over to Ben, because I think I expect he has some thoughts on this.
Thanks, Steve. That was great. So transitioning to the MongoDB focused section of the webinar, I want to just kind of quickly cover off on what the agenda will be for this. So the first thing we're going to do is kind of just talk a bit about generative AI and the role of vector search in it. And then we're actually going to kind of step back and talk about some of the fundamentals of vectors and what vectors are and kind of tools that are used around them. Then we'll talk about Atlas Vector Search specifically, our new offering, and the AI integrations that it has. And then lastly, we'll give some real world examples of where Atlas Vector Search is being used today. So generative AI and vector search. The way we see it is that, generative AI is the next big leap in technology evolution. And so, in the 90s, we saw the internet. In the mid to late 2000s, we saw mobile. And then in the early 2010s, we saw cloud computing. And we see generative AI as being kind of the next big wave. And this was kind of most clearly demonstrated with the performance and growth of ChatGPT in many ways, right? Simply put, the time it took for ChatGPT to reach 1 million users was very impressive and staggering. And it drove people all over the world to take notice and start thinking about this in a much more serious way than they had been before. And what that kind of led to was a question that we were continuously getting from customers, which is, how do you use AI to augment applications and end user experiences in a way that adds value without adding unnecessary cost and complexity? And the challenge is really providing large language models, the kind of new glut of AI capabilities, with the correct data to power accurate and consistent responses, i.e. not hallucinate. And this is where we see vector search entering. And specifically coming to the fore, because the reality is that vector search also has a lot of applications in a variety of different domains, not just AI and large language models. So stepping back, though, as I said, I want to quickly cover off on what are vectors and kind of what do you need to understand about them before you can make use of them. And so a kind of quick definition of vectors is that, vectors are a numeric representation of data and its related context. And what does that mean? If you take a simple example like this string here, a quick brown fox, and its vector, which is kind of this array of floating point numbers, the data is a quick brown fox, right? The word that you see there inside of the string, the letters, everything that's kind of visible there. But the related context are things about that data, right? The fact that, quick is not slow, brown is a color, and it's not yellow. And fox is an animal. These are the kind of things that you can think about when you think about context. And immediately you can imagine that this would be an extremely powerful concept, representing all of this information within just kind of a string of numbers. And so probably the first question you have is, how do you produce these vectors? And the answer to that is that vector embeddings, or vectors, kind of the same concept, are produced by sending data through what's called an embedding model. And this is a machine learning model that you can get from the likes of OpenAI or Cohere, Hugging Face, Google Vertex. Any of these providers can turn your data into vectors. And the way it works is you take some set of unstructured data, like audio, video, image, text, and you send it through this embedding model, and it returns a vector embedding to you. And at that point, you can then utilize those. As was kind of alluded to earlier, vectors that are produced from similar data will form clusters in space. And what does this really mean? Well, if you had a set of vectors that represented Queens, Manhattan, Staten Island, and Brooklyn, and similarly, you had a set of vectors that represented Grand Central Park and, Grand Central Station and Central Park and Wall Street, you would probably see those two sets of vectors kind of cluster into two groups. One that would be NYC boroughs, which was for that first set, and the second that would be, Manhattan landmarks. But additionally, you would also probably see that generally those two sets of vectors also wouldn't be too far apart from one another because they're all places and they're all in New York. And so this is kind of a simplistic way of looking at what we mean by clustering and what is really kind of crucial about vectors that makes them so useful. And so, I will also just kind of call out here that, this is a 2D kind of description of vectors, right? And what we're really talking about is these very high dimensional vectors. And so this is just an easier way to visualize it, but it's important to remember we're talking about thousands of dimensions for these new capabilities that become really interesting. So once you have this concept, though, you can then take advantage of vector search. And I'm speaking kind of the generic capability, vector search. So what vector search allows you to do is it allows you to search through data to find relevant results by utilizing the distance between these high dimensional vectors. It relies on machine learning models to convert your data into these vectors. And then at query time, calculating the distance between the vector for the thing you're looking for and all of the vectors that you've stored. And that's kind of the core of what vector search is. Now, what's important when thinking about vector search is understanding what that distance that I just mentioned is. So the distance between vectors. And the way we see it is there are a variety of ways of calculating distance, but I'm just going to cover three quick ones so you guys have a perspective. So the first is Euclidean, which is the distance between ends of vectors, right? The second is cosine, which is based on the angle between vectors. And the third is dot product, which is based on the angle between vectors, but also includes the vector magnitude or the distance. Now, this is obviously very mathy, but what this kind of breaks down to is that these similarity functions are good for different things. So Euclidean, the first one that I mentioned, is good for dense data, where individual values matter. So you can think about kind of things like image similarity, where an individual pixel inside of an image may be kind of highly deterministic as to whether or not that image is similar to another. Cosine works a bit differently, right? So it's good for sparse data, where orientation is more important. And we see this being utilized for things like text, concepts, and themes. So you could think about kind of situations where one word in a sentence is highly deterministic as to what that sentence means. So that's something that we see, cosine being used for. And then finally, dot product. This is an interesting one where both, you have sparse data and the orientation matters. And we see this kind of coming to the fore for recommendation systems. Now, I'm not going to go any further in on these distance functions, but what's really just kind of important to keep in mind is that the one that's appropriate for you is going to be highly dependent on your use case. And this is probably a good frame of reference to start with, but you'll really want to test and understand how they kind of operate better. Cool. So the last bit is really understanding vector search, which is typically implemented through something called k-nearest neighbors. And typically, when you use the term k-nearest neighbors, we're referring to an exact search over vectors. And that means that you've taken unstructured data, you've created, through your embedding model, all your vectors, and you've stored them somewhere. I'm using the term vector store here kind of generically. Then at query time, you could do a k-nearest neighbor search. And that means you're going to find the distance between the target vector you're looking for and every vector in your store, and then sort them in order of the distance. Now, that's very powerful. But what you might kind of immediately think is that that would be very costly. At query time, figuring out what is the distance from this vector to every vector in my store. And this is what we mean when we talk about exact search, where you get kind of the total list of nearest neighbors to your target. This is useful, but where it kind of struggles is when you get to scale. And that's where we kind of change a bit and take a different approach, which is called approximate nearest neighbor. Now you're still getting a set of nearest neighbors, but instead you're getting an approximate set. And so depending on how you tune algorithms and implement your structure, you may find that you get, 95 or 97% of the nearest neighbors. And that's a term that is often, referred to as recall. So how many nearest neighbors or true nearest neighbors did you get? And the way that this is implemented is, there are a couple different indexing strategies out there, but one of them is called HNSW, which stands for Hierarchical Navigable Small World, which involves a graph-like structure that you can see here in this image, where you have these different layers to your index, and you go into a specific layer, and then you traverse through the layers to find the nearest neighbors and pull out the results. And specifically, HNSW is what we use as part of our solution to provide vector search. But again, it is an approximate nearest neighbor algorithm, which is prioritizing speed over accuracy, right? Instead of getting the exact set of nearest neighbors, you're getting most of the nearest neighbors, and you're getting them very fast for real-time applications over large volumes of data. Cool. So we've just covered kind of all the basics that you need to know in order to really get into what is Atlas Vector Search and how would you go about using it. So Atlas Vector Search is a new solution that we've released that enables customers to build intelligent applications powered by both semantic search and generative AI over any type of data that they store in their database or elsewhere. The way it works is that you store your vector embeddings right next to your source data and metadata. The vectors are inserted and updated in the database and then automatically synchronized to the vector index, which allows you to query them with that approximate nearest neighbor algorithm. You get to query by vector search using a single API that you use to query your data, so the MongoDB query API. So it's consistent for developers building on top of the application. And lastly, vector search kind of removes all of the operational heavy lifting in the form of our battle-tested MongoDB Atlas platform, which I'll go into a bit more detail in a second. But this is kind of the crux of our solution. Now, the way it actually works in practice is that for MongoDB, data is stored in documents, so JSON documents. And the way it could look is you would have a series of fields in your document with a field name like symbol and a value of ABMD. You might have fields like year or date, and then you would have values for each one of them. The last one that you're probably noticing here is this one that says content. And inside of content, we have a string, which is kind of unstructured text, and it says, operator, ladies and gentlemen, thank you for standing by. The way you would use MongoDB to do vector search is that right alongside that content, you would store a content_embedding field. And this would be an array of floating point numbers where the more dimensions you have in vectors in your vector is equivalent to the more floating point numbers. And in each document, you could have a vector that represents kind of some semantic meaning of data in that document or elsewhere. Once that's done though, and you've added your vectors to your documents, you just need to go and define an index. And the way you do this is you specify the name of the field that you're indexing, as well as the type of index, which is KNN vector, the number of dimensions that are in your vectors, and we support up to 2048. So any model that produces a vector that is under 2048 dimensions will work with our offering of Atlas Vector Search. And finally, you use you define your similarity function here in the index being either Euclidean, dot product, or cosine. Once this is done, the index is immediately built behind the scenes, and you can go ahead and query using vector search. In terms of the last piece of kind of technical detail I want to kind of dive into is actually the $vector search stage. And so that's how you go about querying using vector search. We released this new stage, $vector search, at mongodb.local. And the way it works is in the first 3 parameters, you define which index you want to use. You define the query vector, so the vector you're looking for, which is based on an embedding created on top of the query that was provided. So if someone says, great movies, you would embed that, and the vector for that would go into query vector. And then the path, which is where inside of your documents are those vectors living? So what's the field name for that? And those are kind of clear. The next 3, though, I want to kind of double click on because this is where a lot of the magic is really happening. And so the first interesting part is num candidates and limit. So the way to think about limit is the number of results you're going to get back from this stage. So how many results does my application need from this query? And so that's 10. But interestingly, what's partnered with limit is a knob called num candidates. And this is basically a way to adjust how accurate your results are going to be. And what I mean by accurate is kind of what I was referring to earlier when I talked about approximate nearest neighbor. So num candidates is how many different entry points we have into that graph to go into to find the 10 nearest neighbors. Because depending on where you enter that graph, you'll get different results as you traverse through those layers. And so what we've seen in practice is that you want a kind of ratio of maybe 10 to 20 to 1. So you would want, for a limit of 10, somewhere between 100 and 200 num candidates to get really high recall or accuracy for your true nearest neighbors. So that's one bit. And then the second bit is the filter. And the filter is a really interesting capability being tucked inside of this $vector search stage, because what we do here is we do what's called a pre-filter. So as we traverse your index, we filter out the values or documents that don't match this filter. And so the useful part of a pre-filter is that it's extremely efficient, and it also guarantees that you're still going to get the limit that you're looking for as long as things that match your filter exist inside of the database. And so in this example, you would say, I only want things that are year greater than 1995. And you're using MongoDB query operators here to actually do your filtering, which is awesome. As you can see, it's kind of like really just native inside of the overall MongoDB ecosystem with this new filtering capability. And then if you wanted to do something like a post filter, for those of you familiar with MongoDB, you could just think of adding a $match stage right after this. And so you can combine and compose $vector search with all of the other value and richness of the MongoDB aggregation platform or the MongoDB aggregation pipeline syntax. So this is how you go about using it. But what I just alluded to around aggregation is that this is also built directly into MongoDB Atlas, the developer data platform. So with Atlas Vector Search, it sits right alongside the document model and the unified API, where we have OLTP workloads, time series, full text search, analytics, stream processing, and now vector search. And all of this relies on the Atlas platform, which is a multi-cloud, scalable, resilient, and performant security first platform. And so by using vector search inside of Atlas, you get all of these things out of the box. And that's one of the things we're super excited about, kind of combining all of these technologies together to deliver new and exciting experiences for customers. So that's the feature. We talked about kind of some of the prerequisites. We talked about how it's exposed. Now I want to talk to you a bit about kind of how it's used. And so vector search is being used for a variety of things. We mentioned AI, but the reality is that it's being used for semantic search. It's being used for question and answering systems, feature extraction, recommendation systems, synonym generation, image search, as well as others. But one thing that's really exciting right now is how it's being used for large language model memory or retrieval augmented generation. And this is where it kind of comes to the fore around this new generation of AI capabilities and what so many people are excited about. So retrieval augmented generation, or RAG, is really a technique that helps make an LLM useful. And the way you can think about it is that with generic large language models, you have general information. And they're extremely powerful. They know a lot, and they can provide kind of very nuanced and interesting responses to questions, but they suffer from just a few gaps, right? Which is, number one, they have a training cutoff. So the point at which they were trained up to is all that they know. So anything that happened after the fact, they don't have insight into, right? They're missing private data, right? So the data that you and your companies have that is not available for the training set. They can be unfocused and suffer from hallucinations, right? Without additional context provided to these models to help them kind of give good results. And lastly, they're not personalized, right? You don't want to be deploying a different model for every one of your users. That's not really going to be scalable. And so with retrieval augmented generation, you can insert context and focus with this proprietary business data that you have sitting in vector search to focus and improve results from these large language models. So you can insert things like company-specific data, product info, order history, secure user data that you don't want to be providing to these providers to be trained on. Instead, you just want to insert it at prompt time, right? And by combining these things, you end up with a transformative AI-powered application that is refined, consistent, and accurate. And this is really the power of retrieval augmented generation. Now, how all of this works together is really by stringing together your client, the application, vector search, and the large language model. And typically, this is all done through what is often referred to as an LLM app framework. And I'll talk about those in a second, but first I want to just talk about kind of the information flow. So the way this works is a client would submit an inquiry, which would go to the framework. The framework would then send that query over to vector search, and you would get back the related contextual data for that specific query. Then the framework would take that filtered contextual data and send all of that along with the query to the large language model. And so they would have not only what the user or application is looking for, but also the context that it needs to answer that question. And with that, it would do a result back to the framework, which would do some additional post-processing, and then return a result back to the client. This is really the flow of what's often referred to as retrieval augmented generation, but sometimes in-context learning, as a way of utilizing vector search in partnership with large language models. And the way that this is often done is through a framework. And one of the things I'm really excited to mention is that Atlas Vector Search is integrated in some of the most popular frameworks used for building these large language powered applications. We have support in LangChain, Llama Index, and Microsoft Semantic Kernel, and we're continuing to invest here more to add more of these supported libraries. So we've talked about integrations, we've talked about the service, we've talked about kind of core concepts. Now I want to kind of give you some insight into what our customers are actually doing with this. So the first one I want to highlight here is a company by the name of Viso Trust. So Viso Trust is an AI-powered third-party cyber risk and trust platform that helps companies to access, actionable vendor data. And they've had great success using Atlas Vector Search. A concept inside of security is this idea that you have to kind of adhere to some compliances as a software vendor or provider, and a customer buying those services wants to be sure that those are kind of adhered to. But what's interesting is that sometimes there's a delta between the two. And so the provider of the service is going to have some attestations that they attest to that they're doing in order to kind of be secure and private. And the customer is going to have some specific requirements. What Viso Trust is doing is they're using vector search to vectorize both sets of the attestations and requirements, and then providing better guidance to customers who are looking to consume these services by matching these two things up, which aren't necessarily using the same vocabulary to define what they're doing, so that you can have, trust in the vendor that you're purchasing from. Another example is Metaphor. And Metaphor is a data catalog company where they provide, automated support for governance, data literacy, and data enablement through an intuitive user interface and platform. And they were thrilled to find vector search available with Atlas, as they were experimenting with other platforms, but it was much easier for them to consolidate into a single. And they're using vector search as just a kind of straightforward way to improve their search results with semantic search, so searching on meaning, rather than needing to kind of find exact values, et cetera. And so they're using this to just kind of enhance their search capability, and are now exploring even more ways that they can take advantage of this service. And then lastly, we have Extract. And Extract draws on thousands of data sources identified by domain expertise, using AI-powered analytics to locate and track and forecast both digital and physical risks to public safety in real time. And they are specifically using Atlas Vector Search to provide context to large language models to reduce hallucinations and improve the results that their kind of LLM-powered services inside of their app are providing. And so they're having great success using Atlas Vector Search and have been really happy with the service so far, and have seen a ton of value in not needing to bolt on an additional standalone vector database to solve their use cases. So in those three examples, you saw three different use cases for vector search, which I think is amazing, right? Just kind of this vocabulary async need for matching two different pieces of data. Just your kind of classic semantic search for improved search results. And lastly, improving the responses from LLMs by providing context at prompt time. And each one of these customers are using Atlas Vector Search right now and seeing great results with it. So in summary, what have we covered? Atlas Vector Search is built on MongoDB Atlas, which is a battle-tested platform that is fully managed and allows you to develop and run applications anywhere. You store and manage your both source data, metadata, and vector embeddings all in one platform and in one place. You get to take advantage of a unified query API to get one consistent experience of working with all of your data. And finally, vectors are inserted and updated and then automatically synchronized between the database and vector index, so you can build simpler and faster. And with that, that concludes the presentation. We'd love for you to test out the service. Definitely suggest going to Atlas to try these things out. But now we're going to move over to the Q&A section of the webinar. And I'm going to open up the Q&A panel, and bear with me just for a second because there are a lot of questions. Just starting at the top. The first question is, should we expect matrix databases? I think this might be alluding to the fact that they're, kind of vectors, which are kind of, let's say, how would you describe this? Kind of one column of high dimensional numbers. And then there are matrices, which kind of can expand it. And right now, we're not hearing a lot about that. There's definitely demand for kind of like hosting or providing for multiple high dimensional vectors within a single context. But so far, we're not really getting into kind of like the matrix world. And I think we'll see how things evolve, but very much TBD. And also feel free to reach out after if you want to discuss that further. So the second question is, what is a vector, which I think we covered in detail. So I'll consider that answered. Next question is, does this vector DB store structured data as embedding? So I think this was kind of covered in the presentation, but the way our service works is you have your unstructured or richly structured MongoDB data sitting right alongside your vectors, and you get to store and manage them all in a single place. The next one is, what is different about MongoDB Atlas? And I think I covered kind of a few of the unique value props, really kind of the flexibility of the MongoDB document model in partnership with vectors, and the fact that by having this all inside of a general purpose database, you have just a ton of flexibility and ease of use around not needing to kind of string together multiple systems in order to get this really powerful capability. Cool. The next one is a question about graph databases have similar characteristics. What makes them less attractive to vector databases? So graph databases are another way to model data and model relationships. And I would say, actually, I think they're somewhat orthogonal, right? You can use graph and you can use vector. You can model graphs inside of MongoDB, and you can use vectors on top of those graphs. And so I would say I wouldn't kind of view them as one or the other, but potentially two different ways to both model and query your data. And in many ways, we're hearing a lot of kind of interest in just the concept of knowledge graphs in partnership with vectors as potentially providing a lot of value. Cool. So is there, well, actually, I'm going to quickly pause here. Steve, is there anything you wanted to add to kind of the question of graph, or anything you're seeing more broadly around kind of that question and what's going on there?
Not really. I mean, I think, what we'll end up seeing, and we've already seen this from some projects and vendors in that space, is that they're adding vector capabilities. But I think that the core of your answer, and that they are sort of largely orthogonal. There's separate approaches. I think is the correct one, right? And I think, what we've seen in the space, as we talked about, is that there are a variety of different models to attack a variety of different kinds of data. And, they are going to be used in sort of varying patterns, right? It's going to be, we may have, to your point, vectors on top of graphs and so on. So it all comes down to what you're trying to accomplish, but no, I don't think they're certainly not equivalent.
Cool. Yeah, that's awesome. Thank you. Cool. So the next one is there any way to store vectors of more than one field from the same document? So today you can store as many vectors as you want in a single document, as long as it fits within kind of other limits of documents, right? Kind of the 16 megabyte MongoDB document limit, et cetera. What you can't do today is have multiple vectors inside of a single document, inside of a single index. But this is something that we're actively exploring right now. And we see a lot of really interesting ways for this to kind of drive a lot of value. And so I would say keep an eye out. There'll definitely be news about this coming in the not too distant future. And if you have more questions about it, I'd also recommend you go to the MongoDB community forums to ask about it. And myself and other product managers on the team are actively monitoring those. And we will, definitely reach out to chat with you more about kind of the use cases for this. We're super excited about it. And we think it's one of the, very unique value props of document model in combination with vectors. So that's something we're really interested in. Cool. Now, the next one is about OpenAI embeddings, so text Ada002. The answer is yes, you can use those with Atlas Vector Search. Those vectors are 1,536 dimensions, and we support up to 2,048, and so we have a lot of customers using OpenAI embeddings. Cool. Does this also support hybrid search? So this is a great question, and I want to just kind of maybe give some additional context to kind of set the stage for everyone. So with vector search, you can get back a ranking of data based on the semantic similarity that's determined by the distances calculated at query time. In more kind of classic methods of search, which you might also refer to as kind of using sparse vectors, you can do all sorts of ranking and boosting and changing of the ranking of your search results based on text and additional kind of heuristics and rules. The question of hybrid search is often about kind of combining ranking. with vector search today, Atlas vector search, within a single stage, you can do vector search and get back the kind of nearest neighbors in that rank order and filter, right? And so when you're filtering on text. But often when we talk about hybrid search, we're really talking about kind of combining two different rankings of your results. And that actually can be achieved today with Atlas by combining our $vector search stage with our $search stage and kind of merging those two ranks of data. We're actually kind of really actively researching what would be an even better way to implement and use this. And so, if you have questions about this, I would again recommend going to the support forums or community forums and checking in. We would be really interested in discussing further kind of what you're thinking about there and what you'd like to do. There are ways to achieve it today, and we're thinking about ways to make it even easier in the future. Cool. Can you explain a little bit more on the difference between vector databases and vector embeddings? So, vector embeddings are the vectors you create, and then, a vector database would be a place where you store them and do vector search. I think that's probably, maybe was clear from the presentation, but I'll just kind of reiterate that. Cool. So Rajiv, do we have performance metrics, like how many queries per second supported? We do have, a variety of performance metrics. There's not a specific QPS that we have for kind of the service writ large, but that's because you're able to scale and change your service, inside of Atlas with all of the options around scalability. So going between different tiers, taking advantage of search nodes to decouple your, vector search workload from your operational transaction workload. And all of that determines kind of queries per second, as well as the amount of data that you're storing and the dimensionality. And so if you have a specific question around this is another place that I would definitely recommend reaching out to the community forum, and we'd be happy to kind of jump in and help you there. But there's not kind of one single answer there, if that makes sense. Cool. So does the vector database itself possess conversational AI capabilities and provide, responses to questions, or is it solely store data in numerical formats? So the database capability is about doing vector search fast, and we rely on those integrations with the other providers, and specifically via things like LangChain, Llama Index, and Microsoft Semantic Kernel to connect that data to conversational AI capabilities. And so that's the way we see that world right now. Can we know what is typical latency in milliseconds for ingestion and retrieval embeddings? Yeah, that goes along with kind of my answer earlier about kind of latency and performance metrics. Really, you can scale your system to support what you need. One of the things that's interesting about our model in general, right, is that you're inserting data into your core MongoDB cluster, and you can scale your cluster to support ingestion at whatever, speed you need. And then the index is built on the back of that. Unlike kind of dedicated systems where the index is built at write time and therefore kind of throttles or has some contention around writes as the index gets built. And so that's something that's kind of unique about how our decoupled architecture can really kind of add value there. Cool. The theme here looks like similarity in data set. Is that the main purpose of vector DBs? How is this different from a graph DB like Neo4j? I think, that's an interesting question. Similarity is definitely kind of a theme. What I would say is probably a more broad way to put it is distance, right? It's how similar via the metric of distance are points of data. And that could be, similarity of text, but it could be similarity of image. It could be similarity of some obtuse data point, right? And that is in many ways the same purpose of vector databases. The question of like, how is this different from a graph database, I think is probably, within the context of this question, primarily around the need to kind of define relationships intentionally between data, whereas arriving at those relationships between data through machine learning models and embedding that data and determining distance, right? With graph databases, you need to kind of establish those relationships. I'll probably, say that that's about covered. I think I do want to just kind of call out that, vector and graph are, kind of independent or orthogonal. But like within the context of this question, I think that's kind of how I would, carve out the similarity space between them. Cool. So So vector query change according to our documentation field. So the answer is you store vectors inside of your documents and you have full fidelity to update them as you see fit. And you can also use a variety of capabilities inside of the platform to keep them updated in an automated fashion. So it's not automated by default in the sense that, you don't define a relationship between the kind of content field and the content embedding field and then have that automatically updated just inside of the database itself, but you can use tooling inside of Atlas to actually help automate that. Cool. When you say similar, what constitutes similarity? For example, fast and quick are semantically close, but not close in terms of any kind of analysis you could do on their characteristics. So are the word vectors generated with this with this in mind? How is this process carried out? So this is a great question. The simple answer to it is that it's really dependent on how does the machine learning model that you use to embed the data work? What is it prioritizing? How is it defining similarity? And then what distance function did you choose? And so this is somewhat kind of outside of the database in the sense that that comes from the machine learning model. And you really need to use the right model for your kind of approach. Depending on whether it's kind of a strict text model or one of these kind of embedding models based on large language models, it's really about understanding the context of the word and then pulling back that similar data. But that similar data is not necessarily going to give you the answer to what's the answer to fast and quick. So that's kind of the short answer to that. I don't know, Steve, is there anything you wanted to add there?
No, I think that's right. I mean, I think, going back actually to the question about graph databases, right? I think the one of the differentiating, features from a vector standpoint is that you have sort of an additional component here, which is model, right? And the model is going to be the one that determines ultimately sort of what the relationships here are. You have a wide variety of them, as we mentioned, sort of on a per content type basis. But in addition to that, even within individual content types, you're going to have models that are tuned, sort of in favor of different things, and that it's a very different concept, than most of us are used to, right? So, relational, you're defining relationships all up front. Obviously, in graph, it's more on a per object basis, and from a vector standpoint, your relationships are ultimately going to be defined by the model that you apply to it to generate the vector embeddings in the first place.
Absolutely, yeah, totally agreed. Cool. So it's actually 2 minutes shy of the end of our time here, I believe, and we have I think roughly 100 more questions. So I am going to take it to follow up. We'll get all of these questions answered after the fact and send out the answers to everyone from the call. But obviously we're not going to get through all of these today. I'll maybe just answer one more here, just in order. And then I think I will transition it over to the team to kind of close this out. But how are the objects weighted in order to define the initial vector values? Is it a manual process to define the relationships in vectors? So this really gets back to kind of what Steve just mentioned, right? Which is that the models are what define this. What is powerful today is that there are all of these off-the-shelf models that have such a great generic representation of the overall, world of data. And so through them, you don't actually need to be an AI or data science specialist. You can just take advantage of one of them off the shelf, and it has a inherent understanding of text or, whatever medium you're embedding. What we see is that, in the future, people may want to fine tune to get to specific use cases or better results for kind of their specific domain. But these relationships and the weighting is really all defined through the model that you use. And primarily today, we see a lot of customers using off-the-shelf models and, kind of peering out into the future a little bit. We do expect more fine-tuning of those models in general to help people achieve the result that they're looking for. And so I think I will stop there. We're at time. And I'm going to hand it over to Nia from our team to close out.
Thank you so much to Steve O'Grady, Principal Analyst and Co-founder at RedMonk, and Benjamin Flast, Product Management Lead at MongoDB for the amazing presentation. Thank you everyone for joining the webinar today. We invite you to reach out and look for an email from us with the link with the recording made available later this week. Thank you again and have a great rest of your day.